Our topic today is intelligent agents and everything around these intelligent agents. So I'll just first, the way I start is usually I go over the agenda, like what things I'm going to cover, and then I take it up one by one. Like, so I'll just start with that. So the agenda for today is we'll just start with an overview, like what intelligent systems are, how agentic systems fit into this intelligent systems, what are its definition, characteristic. With this two topic, we'll cover all the basic thing, all the terminologies, all the basic things, so that when we move on to the further topics, when I speak, let's say I say multi-agent system, so we should be aware that what multi-agent systems are. And this particular topic is very close to me because intelligent system is something that I have been working right from my college days until the job. This is what I'm today working on. It is very interesting topic. It is growing and there are a lot of opportunities over here. So I'll basically like try to clear your basics in the next 15 to 20 minutes. I won't go too much into basic on what systems are. I am assuming you are pretty aware of that. I'll just go with what agents are, what are multi-agent system, what are these terminologies that I'll be using, and then we'll be moving to different things. Now, one thing that I just want to make it clear that we'll have open discussions here. So in all my slides, I have kept a topic for open discussions. Now, that is how I proceed. And question answer sections can be after each topic itself. Now, if let's say like it is clear enough, we don't want to do that, then what the second thing we can do is we can put everything at the end. So we can finish up all the topics and take up the question answer session at the last. So that depends on you. Like once I finish the first topic, I can wait for some question answers. If we have questions, we can cover it over there. Otherwise, we'll move everything to the last and we'll finish up all the topics. So that is how we are proceeding. But right now in our agenda, if you see the left side, the first two things, overview, intelligent system, and definition and characteristics. Basically, these two topics will clear out our terminologies, basics, and then we'll move on to what are the examples. I have put up case studies in between so we can compare real life examples with whatever, let's say like rational and rationality and rational agents. So we'll have a case study of a real example with that. Similarly, types of agents will have some case study with that. Performance measurement will have some case study with that, and we'll compare it with a like a real-time systems, how it is being implemented today, right? So with that, I'll just move on. So these are the three things I'm expecting, like this is what we'll be getting out of this lecture. First is like we'll introduce the concept of intelligent agents, and I'll also explain the role in AI. So the explain the role in AI is because today all the AI system are part of an intelligent are all intelligent agents, any kind of AI that we can think of, right? And I am currently working as a MLOps professional whose work is to build the systems end to end, not just doing a R&D on any particular algorithm, but using pre-existing algorithm to build systems. So that is where I shine. So I'll be showing you like in my work how what is the role of intelligent agents and AI solutions basically, right? The second objective is understand all the fundamental attributes that make a system intelligent, right? Like autonomy, reactivity, productivity, and social ability. It should be autonomous. It can be reactive to external stimuli. It can take proactive measures to handle difficult situation or challenging situations, and how it interacts with people, it interacts with its environment. So that's social ability, right? So these things we should be clear by the end of this lecture. And the third objective is like basically we should in depth understand what is rationality, what are the different types of agent, performance evaluation, how do we measure how an agent is performing, and what are flexibility and why is it important in a intelligent agent. So these are the topics that we'll be covering now. Now coming to the basics, right? Agents and intelligent agents. Now the first thing is like what agents are, right? Agents are any kind of like, so agents are not the entire system. So agents are a particular part in the system that can take a decision, right? Or they're programmed in a way to take a decision based on a trigger. So there are two things here. One is trigger and one is action, right? So agents are something which has one trigger and one action. So they're autonomous entities. Whenever they particular encounter a particular trigger, they take an action on behalf of that. For example, let's say today we see a lot of chatbots, right? When we send a hi, they suddenly get activated. They say hi, how are you doing, and those kind of things. We ask question, they understand the question and answer. So our hi is the trigger, and that enables the chatbot, right? Similarly, we all are using social media platforms, right? when we click a particular object, we get a lot of targeted videos, we get a lot of targeted ads. So these targets are also on behalf of our click on the screen. So our click on the screen is basically a trigger that engages other inbuilt system. Like there are multiple systems that is working. Like one system will let's say, I'll give you an example over here. Let's say I clicked on shoe, right? So one system understood what the picture is that I clicked on. So it understood that I clicked on a picture of a shoe, or I said something related to a shoe. Once it understands, it sends it to another system. The second system, what it does is it looks for what kind of targeted ads we can provide on shoes. It finds out the best, and then it basically sends that ads to me. So there are multiple systems involved here. So everyone is intelligent, they have like an autonomous thinking, what kind of things we can do, how we can approach the users, and they take a decision on that. So coming back, these are what agents are. So agents are like autonomous entities that can perform a single task or multiple tasks on behalf of a user, right? Coming back to intelligent agents, so the only thing is intelligent agents are aware of their like, so intelligent agents are aware of their environment. So that is the difference between an agent and an intelligent agent. When I send a hi, so the agent will reply hello. That is a normal agent. But let's say if I say hi and the agent is replying hello Amrit, so that we can say that is an intelligent system, or that has been, so that has been triggered in such a way he knows who he is talking to, right? So he knows what he is doing, what his target is. Suppose I say that I am having trouble, so he will connect me, he will understand what kind of trouble I have, he will connect me to a specific person who can solve my trouble. So these kind of things are intelligent. Autonomous driving, right? He can see what's happening in real time, take a decision, and then he can move, whether to steer, whether to take a break, whether to accelerate. He can understand the environment and then take a decision. So these are called as intelligence agents. Now, what is the difference between an agent and a system? So, agent is designed to perform a specific task. A system is designed for a specific purpose. It can involve a single task. It can involve multiple tasks, right? So, for example, let's say a hotel man. I'll take an example of a hotel, right? In an hotel, we have a receptionist. We have waiters. We have got cooks. We have got a lot of other folks who are working in the hotel, right? So every staff, everyone we can think of as an agent with their own specific task. A client comes into a hotel, he goes to the receptionist. So receptionist takes all his details, books a room for him, shows him what the way of the restaurant is. If he wants, he can go to the room. If he wants, he can go to the restaurant. If he goes to the restaurant, he will probably meet a waiter. This waiter is a second agent who will basically talk to that person, that what he wants, what he needs. He understand the need. The cook basically designs the food according to the need of the client, and then the food is served to him, right? So there is a finance system where he pays. So everything is an agent in itself. They come together to build an entire system, right? So autonomous system, these are self-governing system capable of making and executing decision with minimal human intervention. Here, that autonomous system, multiple agents, right? They're built on top of basically, like, I think we are clear about what agents and intelligent agents are. Now, autonomous systems are basically a group of agents working together to complete on a single purpose. Basically, like the example would be a hotel management system where there are receptionists, waiters, there are cooks. So everyone is working together to serve the client, right? The client goes to a reception, he gets a table, orders the waiter. Waiter has its own task. So these are like each receptionist, the waiter, and the cook. These are basically the different agents who are working on a single purpose, that is to serve the client. Okay, so that is what autonomous systems are. So they are like self-governing system which are capable of making and executing decisions with minimal human intervention, right? When we say autonomous system, so these are what system is, the hotel one. But autonomous system is where there is a very little human touch points, right? Mostly it's all, everything is automated. One step triggers the other step triggers the third one. So that is how it works. Now, coming to the fourth one, which is the important one, that is the agentic workflows. So basically, like, we get confused a lot of time, or this is something new. What are agentic workflows, which are not a lot talked about? So basically, autonomous system are not directly built on, right? So, so these are like big system, huge system. Let's say your entire payment gateway, right? So I'll take an example which we all do, right? We all make some UPI payments. When we make a UPI payment, it's not just we send money to someone, right? There are multiple agent systems aware of that. As soon as you go to your app, it authenticates that this is the user who is trying to pay. It authenticates using your UPI pin code and those kind of. So you have a MPIN, so it uses that pin to authenticate. Yeah, this particular user is trying to make a payment. It tries to authenticate your bank account. Then you enter an amount. That amount then travels through a system, a very secured gateway, and then it gets deposited. There are other systems which confirms whether something has been deposited or not, whether it's pending. It checks the status again and again in a few milliseconds. These are like very complicated systems, right? So you cannot just go ahead and build them like, okay, I'll start with this. So what you do is, that is where agentic workflows come into picture. So agentic workflows, as the name suggests, they are like abstraction architecture, right? So suppose I want to build a home. I won't go ahead and I'll just start putting up bricks, right? I'll call a architecture. I'll discuss a plan with him. He will show me a plan. I'll agree to some. I'll not agree to some. He will revisit the plan and he'll come back. So this is what the plan is. So that particular plan is called as a workflow. So suppose we are trying to build an agentic system, then there are. So I'll come back to this agentic workflow at the end again after we went through what are the environments, what are the basically performance measuring metrics. So based on this, I'll come back to agentic workflows of why we need to have agentic workflows in place. But for now, for a purpose of definition and understanding, these are basically the plan, the architecture, and the abstraction that we will use to build our autonomous systems, right? And then the last one is multi-agent systems, right? So I just wanted to have an open discussion here. Like multi-agent systems are basically system that uses couple of agents working on a single purpose, right? So I gave an example of a hotel management system, but I would like to, like, if we want to make this interactive, I'll like to hear from you. What do you think is another example of a multi-agent system, like in terms of an actual autonomous system like payment gateway, hotel? Do you have any other examples in your mind? Okay. So basically, like, we went through some of the key definitions earlier. Now, some of the key characteristics, right? What are the key characteristics of intelligent agents? So these are the four pillars, what you can call. One is they should have social ability. So that is the ability to interact with their surroundings, their environment. So suppose, let's say it's a take an example of a self-driving. Okay, for social ability, let's take an example of a chatbot, right? If I say hi, he knows what to reply, right? Hi. So if I say I need help over here, he knows what is the thing that I'm requesting, right? So that is basically a social ability to interact with its environment, right? Autonomy. So autonomy is basically the ability to take independent decisions without a human intervening it, right? So for example, if a car, if it is a self-driving car, it is moving. Now suddenly there is a person in front, so it should have that ability that it will take a decision that I need to stop over here because a person is crossing, right? So that is autonomy. Now reactivity. So reactivity is basically, let's say there is a system. Okay, so one part of the system failed. The entire system should not break down immediately, right? It should take some reactive measures. It should basically perceive and respond to any environmental changes in real time, right? If, let's say, it is designed to work in a very clear system, and let's say we have a self driving car. Again, I'm taking the same example just to make it very clear. We take the example of self-driving car. Now a self-driving car, let's say it cannot be trained to work on very clear streets, right? Let's say if there is a bump on the street, if there is a pothole on the street, if there is like fog on the street, so these are like various environment changes. If these environment changes happen, our system should be able to react to them. And reaction not always means it should always take a proactive measure. Like, that is what our next point is, taking a proactive measures. But in reactivity, it's basically like it could be as simple as prompting the user that this is a difficult situation, could you please take control, right? That is basically the reactivity. Now coming to proactivity is when it sees fog, it will turn on the fog light. So that is proactivity, taking an initiative to achieve the long term goals, right? So this is basically the different pillars that your intelligent agentic systems are built on. Okay, we'll come back to any questions on this slide. I'm just moving on. Now, these are like some examples and illustrations. Now, basically, what I'll say is like we'll start with the right diagram. Okay, so first is self-driving cars that I was giving an example. So, self-driving cars are autonomously navigate while interacting with the environment. There are a lot of factors. There are people moving around. There are the road conditions are there. So, with these factors, the system should be intelligent enough that it can take its autonomous decision and move forward, right? Similarly, another example of an agentic system is online customer service chatbots, right? So chatbots, you talk to them, they connect you with customer care, they fetch your order details. So there are a lot of things involved, but they autonomously interact with users. So that's why they are also agentic system. Even going to very basic thermostats, right? In your room, there is a thermostat. Why is that an intelligent agentic system? Because based on, let's say, based on your temperature, your environment, so it has sensors, right? So as it senses that, yeah, there is so thermostats are in their AC. So today all the automatic ACs and fridges, they have this thermostat. If it is getting too hot, they will make the environment as too cool in order to make the balance. If the environment is cold enough, they will put it on a little high temperatures so that like everything is balanced in the end. So even this basic thermostats can be considered as intelligent system because they're taking input from a sensor and they're taking action based on that, right? And the last one, I would say, like from an example perspective, recommendation engines. You're working with social media, so your Netflix recommendations, your social Instagram feeds, everything are basically like multiple agents are working together to build this recommendation engines for you, right? Now, basically, like if we talk in terms of autonomous agents, we have got software agents like a web crawler, right? So suppose all this chat GPT and everything, they are trained on huge bulk of data. Now, how do they get this data? So they have written web crawlers which automatically goes to various websites. They pull the URLs, they go to the website, they scrape the website and get the data and then train the model, right? There are software agents. There are robotic agents in manufacturing industry, like autonomous detection of any kind of anomaly. So there are agents for that. There are agents for wrapping up something. There are agents for packaging. So multiple robotic agents are working together to make sure the manufacturing. We have got Google Assistants. We have got chatbots. Every today, almost every app like Swiggy, Zomato, everyone uses a kind of a chat assistant, right? These are like some of the examples of autonomous agents which can intelligently take decisions and work on it. Now, coming to a very important point, what is rationality and rational agents, right? Now, as humans, for us, rationality is doing something right. Okay, so what is this right thing? That is what we are taught since we are kids, that this is how you should behave in this situation. So that is according to us what rationality is. But according to this intelligent system, it is a little bit different. I'm just reading through the definition and then I'll explain what it is. Rationality refers to the agent's ability to choose action that maximize its performance measure, right? So for it, basically, let's say a system is built. Yeah, a system is built to, let's say, let's take an example of a financial trading bot, right? We have created a system that can automatically do trading for us, right? So the purpose of this bot is to basically increase the profit, right? So that is what its purpose is. So by definition, what this bot will do is it will, so its rationality is how can it maximize the profit. Its rationality is not basically taking some good decisions, right? It's taking good decisions that will basically improve its profit. So that is the rationality of a agentic system, right? Given what it perceives about sorry, essentially a rational agent does the right thing to achieve its goal. It doesn't necessarily do the right thing, right? It does the right thing to achieve its goal. So that is the key point here. Okay, now what is the mechanism? Okay, so what happens is we design a lot of metrics. Like let's say we are building a system that identifies whether it's a dog or it's a cat. So we design a test system where we ask him to predict a lot of dogs and cat, and based on its prediction we measure what is its accuracy. So this accuracy could be a performance metrics, right? So based on this performance metric, a model decides what is rational for it. So the rationality for that model is to have a high accuracy. So whatever it can do to get higher accuracy is what the model will strive for, right? And how does it happen? That can be seen in the diagram on the right, right? Feedback and learning, right? So a model should be able to adapt by learning from past experience. Let's say that model, let's say from Netflix. Okay, Netflix recommended a movie to you 5 times, but the user never clicked once. So it got to know that this is a mistake. This kind of movie is something that the user does not like, right? So what it will do is it will try to recommend some other kind of movies. And when you kind of see those movies, you click on a movie and actually watch it, it knows that this is something right. So that is the feedback that it is getting. And based on the feedback, it is trying to learn. It is trying to learn by its past experience. Suppose, again, taking another example for this, you have to predict whether it's a dog or a cat. You predicted correctly. That is a reward. You predicted wrong. So that is a penalty. So based on this feedback, it will learn where is the right direction and where I should go. Right. Second is goal driven behavior. So ideally, it should focus on achieving the object, right? And it can do some trade offs for that. For example, let's say I am building a system that will predict if a person has cancer or not. Okay. In that particular case, accuracy is something very important. But also, what it is important is because based on a cancer detection system, now, what happens is if we say a person who has cancer, if we miss it, that could be very critical. But if we say a person who does not have cancer, if we say that, yeah, this you might have cancer, he will go to a doctor and doctor will invalidate that. So the risk is less. So this is what the model should, the intelligent system should understand. It can take decision according it. So in this particular scenario for this cancer detection, it has to maximize its potential to predict whether a person can have cancer. Okay, if he does not have cancer and he still says yes, we can still manage. But if a person has cancer, we should never say no. So that is where it needs to maximize it. So it should understand what its goal is, and it should have a goal driven behavior, right? And the next thing is decision making under uncertainty, right? Let's say a model is designed to work based on 20 parameters, right? And let's say four of the parameters are missing. The model should not fail over there. Like when I say model, it's basically the system, right? You have built the system. The system should not fail when few of the parameters are missing. It should have appropriate error handling. Like how do you handle this situation, right? So there are different things that we do. We do smoke test. We do a lot of different kinds of testing in order to make it robust. But basically, it should be reliable. Let's say you are working on a autonomous driving vehicle. Ideally, it is trained that when it is green light, you should go. But if a person comes in front of you, it should not just go ahead because it's green. It should be able to suddenly make a decision, immediately make a decision and stop the car, right? And when it's stopping, it should also consider there are multiple cars behind it. So it needs to assess everything and then take a decision. So this decision making under uncertainty. So this is what utilizes probabilistic methods, like what is the probability if I go ahead? What is the probability if I stop right now? Which gives me like more confidence, and based on that probability, it will take a decision. So these are the things that make sure that a model is rational, right? And the agent is a rational agent. Moving on, these are like two case studies that I was thinking of talking, but I think I covered the left one. How to optimize. So the left one is basically, let's say a car is moving forward, right? Now it's a green light. So it has three things like should I accelerate, should I brake, or should I steer? When should I accelerate? If the road is empty, it's a green light, I'll accelerate, right? If it is a green light, but there is a person standing right in front of me, I might need to brake if it came suddenly. But let's say there is a person standing at a certain distance. Maybe I can steer a little bit towards right and left, navigate, and then move on. So these are the decisions that it continuously makes. Like we as a human, we have been doing it all our lives. But when we are building a system, we need to make sure that it has that particular capability where it can optimize the performance. If a person is at a distance of 200 meters, I don't need to immediately brake. I can just steer right? If a person is at a 50-meter distance, I need to brake immediately, right? If there are no person, I might, and if the road is empty and I'm under my speed limit, I can accelerate a little bit. So all these things, it should basically, its goal is to optimize its performance. That is to make sure that the person reaches the destination at time, right? And it can take all different decisions to make that happen. And that is basically its rationality. Like how can it ensure that a person reaches its destination with complete safety? It cannot trade off safety, but it will minimize the time to reach the destination. If there is a better way, if there is a traffic in some point, it'll try to take the person through a road that has less traffic, right? So those are basically the rationality in the models, right? Coming to the right side diagram, task prioritization and scheduling. Now in order to take a rational decision, let's say the second case, I'll take a case study of how about a personal assistant. Let's say we have a Google assistant, or let's say we build a system that will predict how you want to spend your entire day, right? It is your personal assistant, and it is trying to predict what task you need to complete, what task you need to prioritize, and those kind of things, right? So it will create some kind of block diagram like we can see in the picture. What are the necessary tasks, but they're unwanted, right? What are the immediate tasks that we need to complete because other tasks are dependent on it? Okay, what are the preferred leisure activities? Like some tasks that we can do in leisure, we don't have to take it right away, but it might be enjoyable, right? It might give a moral boost to the person, right? What are the low priority chores? And based on this kind of decision making, they come up with a task for entire day, right? So their rationale is basically to ensure that this particular person can complete most of his task without getting burnout, without failing to complete a lot of tasks. So it will prioritize like dependent tasks first, and then it will prioritize the next set of tasks. So this is the rationale of that system. His goal is to ensure that that particular person has particular task lined up for him, and in what order it should be lined up, and how he should take it. It should not be task after task. There should be some leisure activities in between to remove burnout, right? So that is the case study over here. Moving forward, the next thing is what are the different types of agents, right? And so what I have done is I've just tabulated everything so that later if you want to refer to this slide, you can easily do that. But these are the five major types of agent. There could be other agents, but these are the major ones that. So when you're defining a system, you define what kind of agents should I have. So this is basically the types, right? First is a simple reflex agent, right? It just operates on very few conditions, right? It, let's say, basically I say hi, the chatbot will say hi back to me. So that is a very simple reflex. As soon as I say hi, he will say hi back to me, right? A basic thermostat, right? Whenever the temperature goes up, you basically make the AC more cooler. If the temperatures come down, you make it a little bit hotter, right? There's just one task for you. It's as simple as that. If this happens, do this, right? So these are like simple reflex agents. Then we have got a model based agent, right? Model based agent is basically they'll have some internal modeling. For example, if you see the example, there is a robot vacuum, right? In order to clean your house properly, it should have the map of your house. So there is one dependency. But so if it has the map of your house, it can go in, it can track the changes, like, okay, I have cleaned this part of the house, these are the four part I need to clean, it will move to the next part, right? Those are called as model based agent, where you have a model, your house, basically your map of your house is the model over here, and then it is trying to track the changes and make decisions if all the goals the entire model has been properly navigated or not, right? The next one is goal based agents, right? So here you have a goal. For example, even okay, let's take the example that I have provided here, a chess playing AI. So your goal is basically you have to win, right? So your every move, so this is basically like playing chess with a computer. You play a move, the computer plays a move. So here the purpose of the agent is to take every next step such that the next step is towards your goal, which is winning, right? So the computer is trying to win, you are trying to win, and the only purpose of that particular algorithm is, as soon as a player makes a move, I have to make a next move such that I win and player loses, right? That is goal based agents. The next one is utility based agents, right? So here we assign a measure of goodness, that is utility, like to different states. So what happens is, let's say a financial trading system, right? So here we have some utilities, like we have to check what is our profit, what is our losses, right? In order to reach the goal, our goal is not just winning, right? We have to minimize the loss and we have to maximize the profits. We have to invest in multiple things. Overall, we should have higher profits. So it will basically assign that, okay, even if we can get loss here, we might get profit here. Based on that, it will trade. So these kind of things are called as utility based agents. And actually the name is because, not just because like there are multiple utilities, but because they uses a lot of different algorithms, like loss minimization algorithm, profit maximization algorithm. What are the events happening, so that based on the events they can decide what the profit and loss can be, right? So these basically they have different utility tools in order to achieve that. That is how it goes forward, right? And the last one is basically learning agents, which might not be very accurate, but over time their accuracy improves and they adapt to the changes. And the example would be again like modern recommendation systems like your Netflix, your social media, Instagram reels that we get. All these are like learning agents, right? What we have to so what the models are trained to do is they are trained that you are not an accurate thing. You learn from, you keep on learning. Every time a user clicks on something, you learn something, right? You keep on learning and keep on predicting. So there is no end goal over here. It is just continuous learning and being better, better and better, right? So these are the different types of agents. Going forward, this is how basically this is one of the important factors of the agents in itself. What are performance agents? So basically this is basically like measuring the accuracy of an agent, just to keep it very simple, right? Performance is typically measured in terms of how well an agent achieves its goals, not be only accuracy. So accuracy could be one of the measures, but how, what kind of, so it there could be 20 different measures, right? It could be accuracy, it could be like customer satisfaction could be a measure, it could be like how long do you take to reach your goal, that could be a measure. So you basically say that I need this task to be done in 5 seconds, whether or not my model can do it in 5 seconds, that is a measure. So you put a lot of checks to understand if a system is working good or not, right? These are called as performance agents. So mostly these are used in AI. So in AI this often involves defining a performance measure that is a quantitative metric, like this is the time that you need to achieve in, this is your latency, so this is your maximum RAM that you can use, this is the maximum accuracy that you can get, right? All of these are like some numeric metric that are defined, and the goal is to achieve this metric, right? Now we have already covered performance metrics, so this I'll just read through it. These metrics can include accuracy, efficiency, speed, resource consumption and overall utility, right? For example, in a self-driving car, metrics might include safety records, route efficiency and passenger comfort, right? When it says safety records, it could be like some of the rules, like this is like it should be we have some safety ratings, we have some safety records, there are a lot of different terms, right? The end goal is we have to ensure that the person is safe, anything around its environment is also safe. And then the next is route efficiency, right? The route we are taking, is it efficient? Now when it is efficient, you will need to compare basically like whether the time taken is optimal or not, whether the fuel consumption is optimal or not. Let's say you have a longer route but the time taken could be less, right? Then you have to compare like where do you want to put your bias, where are you okay with sitting in traffic but your fuel consumption will be less, or you want to go through a empty road but your fuel consumption will be high, right? So these are decisions that you need to take, and you will have some metrics to define what kind of bias you want to put in this particular systems. Coming back to the case study, the first one is basically it's a trading system. Like we are giving a lot of example of a trading system. Now the performance of a trading system is evaluated based like what we were talking earlier, right? We have to maximize the profit and minimize the risk, right? Then the balance is often represented at a utility function, because these are utility agents, so it's a utility function that the system tries to optimize consistently. So when we say optimize, basically it's okay, how do I give an example? So let's say we have to reach somewhere at 20 seconds, right? And we are reaching, maybe let's say sorry, we have to reach at a destination at 20 minutes. We took 30 minutes to reach the destination, so we have the 10 minutes lag time basically, right? And let's say we arrived there earlier, so we have the 10 minutes of lead time. So there is this 10 minutes plus and minus, that is basically an error or a positive error or a negative error. So basically what this model tries to do is it tries to optimize it. What can you do next time to minimize the negative errors, right? So that so it will have some metrics like calculate the errors, so calculate the time difference in this case. If it is accuracy, if I reach the destination correctly, like suppose I throw a ball, the ball should drop at X point, right? It dropped near to X. What is the distance between the ball and where it dropped? So here distance is a performance matrix, right? So this is what the case study, like this is what optimization is. You optimize the next time you throw the ball, it should be more closer to the X position, right? Coming to the second case study. Now imagine a ride sharing platform like Uber, right? Now this uses AI powered performance agent to optimize driver allocation, right? So there are a lot of metrics that come into for us. It should not be like me get a cab easily, right? It will check what is the demand of the cabs in that area, whether a cab driver is getting paid properly or not. Customers should be satisfied, so it should minimize the time to book a cab, right? It should minimize the wait times, right? Once you book the cab, how long it is going to it so okay, take an example. You book a cab, the cab got booked immediately, but it took 30 minutes to reach to your home. That is not an optimized system, right? You can take 5 more minutes, but you can find a cab that is closer to your home, right? So you have to optimize it in that particular way, that your wait time should be minimal, the driver's distance should be minimal. So if a driver has to travel 4 kilometers to pick you up just to drop you like after 200 meters, that is not optimal, right? So all of these things it needs to minimize and optimize. So this was a case study on like how or like ride sharing platforms work. But if you see on the right, just on a like a TLDR, risk management emphasis, profit maximization focus. This is what it usually measures in a financial trading system. But on a ride sharing platform, it will take wait time minimization and customer satisfaction focus, right? So based on different things, you have different performance metrics and you try to optimize that. So I hope this is clear. Moving forward, now what are task environments, right? So whatever systems you build that are going to work in an environment. For example, I'll just read through the definition first. The task environment is the context or setting in which an intelligent agent operates. It includes everything that the agent interacts with, the sensors, actuators, and the rules that govern the environment, right? Now coming back to an example first, and then I'll move to the different types. Going to the environment, right? First, the environment is, let's say on a self-driving car, the environment is basically where the car is moving, the road, the traffic lights, the people walking on the roads, right? The road conditions. These are the various different things that will affect your ride, right? The traffic on the road, the distance between the next car and the car behind, the distance on the right side, like a car is moving. So it has to like take care of everything, right? So it has to so going back to the definition, the sensors. So the car, the automatic driving car, it will have sensors. Like the sensors will give the distance between the different cars. There will be cameras that will say where people are positioned, right? What are the rules? If people is positioned at this distance, I have to slow down. If people is situated at a very farther distance, I have to steer away, right? These are the decisions that will take based on the rules. So every external stimuli is basically your environment, right? Now this environment can be divided into 5 different types, right? First one is I'll go with the right side bottom, right? Observability. Let's say our car is moving on a road, right? The observability determines whether environment is fully or partially observable, right? Impacting strategical development. Let's say your car is moving, but it is moving on a very foggy road, right? So it is the rules are designed that if you see a people on the front, you have to slow down, right? If you don't see a people, you can move ahead, but in a foggy road you will not be able to see people until they're too close, right? So the your intelligent system should be able to take decision in this kind of observability as well, right? It can slow down. Like there will be some by default logic. If it is too difficult for you to capture anything, you need to slow down, right? Then there are episodic versus sequential. Now what that means is basically, let's say, so basically this comes in a multi-agent system. So you have multiple steps in a job, right? Let's say you want to go to your destination. First you need to navigate what is your path is. Second, you need to so these are independent. So navigating your path, that is independent, and then moving forward. So while moving, every time you try to find an optimized route, right? So these are working parallelly. But let's say you are going to, let's take the example of a travel booking app, right? Where you are automatically you are going to a website, you are asking that I want to go to Himachal. can you give me a list of all the places that I can visit and which hotels I can take, right? In that case, what it will do is first it will take the place. So the first is the place, then it will move to what are the closest hotel to your travel. Let's say you're coming from railway, what are the closest places hotels to the railway station? Once the hotel has been finalized, from this hotel, what are the different places you can visit, which are the nearer places, which are the farther places. So this is like a sequential. You complete one task, based on the output of the task, your next task is defined, right? Then you have got discrete versus continuous, right? So whether like let's say what kind of data, so the complexity of a state, right? For example, like this is we all are EC term, so our environment is like can be defined in a blocks or something or not, right? Is it a continuous environment where I have to continuously make decisions? Is it a discrete environment where I can make a decision and then follow through it until I have to take a new decision, right? Something like that. The next one is determinism, that is affects predictability of outcomes, right? So based on like certain data, so if a person suddenly comes in front of you, I should be able to take a decision on my own that I have to stop right here. So that is basically as simple as the determinism. And then static versus dynamic, it relates a little bit to the discrete versus continuous. Like so you can take a static decision, you can move forward with it, but let's say you are so suppose, how would I say, static, let's say chatbots, right? They're more towards a little bit static initially, like the older chatbots, right? You say hi, they'll say hi. You say I have a problem, they'll say for this problem this is the solution, or they'll reply I don't understand your problem, right? Dynamic is a little bit different, where it kind of understands your problem, it thinks and then it responds, right? So it adjusts itself, it doesn't give you a repetitive answer, something like that, right? Moving forward, factors affecting the task environment. So this is basically what we were covering, but I have given all the examples over here. So when you have the slides, you can probably move through it, but you have like all examples and all the environments. So you can just read through this. I'll skip this for now. Now linking, yeah, the next one is linking environment property to agent design, right? What are the design considerations? The nature of the task. So basically, so this is where the workflow comes. So we were talking about agentic workflows, right? So this is where the concept of agentic workflows come, right? When you are building a system, so first you need to come up with the architecture, and then you have to link the environment with that architecture. So these are the environmental constraints. Okay, based on these considerations, I have to make my workflow, and then I'll implement my agentic system. For example, in a dynamic and partially observable environment, agents must incorporate learning mechanisms and uncertainty handling, right? If a car is moving on a foggy road, so it has to be very like it has to be very sharp at taking decision. If a person suddenly comes in front, I have to immediately stop. I have to always monitor what is the distance between me and the car behind me, right? It has to be very considerate about its nature. Second example, a robot designed to search and rescue in disaster scenarios, right? It must deal with continuous change. Anytime and there could be a new obstacle coming. The entire environment could be changing again and again. There could be building falling, right? So it should have sensors, it should have processing algorithms and decision-making logic that are tailored to handle this kind of situation, basically, right? Moving forward, flexibility in intelligent systems, right? So based on the previous, so we discovered that there are these many factors that are affecting the task environment, right? So we should build systems who are flexible. Now what does this mean, and what why this, that it can adjust based on so ideally in this slide what we want to do is, what is the flexibility? That is flexibility as in, can an agent modify its strategies or actions when confronted with a challenging situation, right? If there is some challenges that was not unforeseen, can the model adapt to it, right? Rather than being rigidly programmed like this is how you should behave, it should be if the scenario changes, you should have the flexibility to change. A system or an agent should be able to adapt based on its conditions. So that is what flexibility in intelligence agents, right? Now why flexibility matters, right? Because just think of it like in a real world situation, that like all the systems, if it is a AI system, it will be trained on data, right? If it is a non AI based system, if it is a manufacturing system or something like this, so your manufacturing process changes, so the change is inevitable, right? So we should build system that should be reliable, that should be scalable. Basically, the term will here will be scalable, right? It should not stop working if some external factor changes, right? It should be able to work for a very longer period of time because it should be goal oriented. It has to finish the goals even if the underlying parameter changes. I should be able to adapt it. I should be able to move on. So that's why it matters a lot. Moving on, basically how to achieve this flexibility. So these are the three things we can do. One is, if it is a AI based system or an ML based system, we go for adaptive learning, right? We keep on learning from our mistakes. Even in non AI system, basically, if you know what a mistake is, you keep on adapting to it, you keep on learning to it, right? Second one is environmental modeling. When you build the system, you take consideration of the environment parameters and then you model your system accordingly. And the third one is modular design. And this is a very important system. You must have heard a lot about decoupled system, right? So this is what it comes. So every small task should be a module in itself. So let's say you have one system. Ideally, the recommendation is to work with multiple agent. You don't just build one agent to handle a very complicated task, right? You build multiple agents. Each agent has its own specific task, such that if a single agent fails, the entire thing do not break down, right? You'll have error handlings, right? Who will prompt you that this particular thing has broken. Our accuracy might be affected, but it should not immediately break down and stop working at all, right? That should not be. So it should have a very modular design, that it should have a plug and play design. That is what it is. So if you have this kind of system, it will make your system much more flexible. Moving on, there are just few case studies. The first two is something I'll explain. The third one, you can take it as an assignment where you can do a little bit of study on how we can make a social media recommendation system as a like case study for a flexible system. What are the performance metrics, and you can take that up. But I'll just explain the first two, right? The first one is, consider a virtual assistant that not only responds to your immediate queries but also learns your preferences over time, right? Let's say you use rather than like just imagine, like rather than going to Swiggy and just looking for your food and ordering, how about you just ask a chatbot that I want to eat this XYZ particular food? Okay, what you can do is he will automatically browse through the restaurants. It will automatically see the ratings. It will automatically see the prices based on the optimization algorithm that we were talking earlier. It will optimize where we should order the food based on the distance, the delivery time, the ratings. Okay, and it automatically orders food for you, right? And over time it learns your preferences and it suggests that today I think you want to eat this, right? How easy it will be, right? That is one of our like biggest headache. On we go to app and then we keep on deciding what we want to eat. Similarly, on a movie platform, we go to a platform and then we kind of keep on thinking what kind of movie do we watch, right? And these systems can help you help you walk through that based on your preference, like, so the recommendations will be very much personalized, right? So this is an example of flexibility, right, through adaptive learning. Now, coming to the second case study, imagine a city's traffic control system, right? So if you hard code your traffic control system that, yeah, you have to stop for 20 minutes, the other side will stop for the next 2 minutes, the other side will stop for the next 2 minutes. Now, let's say one of the sites doesn't have a lot of traffic, but the other side has overloaded traffic. What happens is a manual human has to come in, a traffic police has to come in, turn off the light and handle the traffic in peak hours. If we have an intelligent agent over there, what it will do is it will analyze, yeah, I don't see any traffic in this road. It can use some kind of object detection algorithm to identify how many cars are waiting, right? It can decide, okay, there are not a lot of cars waiting, so I'll probably stop this particular road and I'll let the other road go through, right? So that way your traffic congestion can be handled very efficiently. So that is again flexibility. This showcases flexibility by responding to unpredictable events and continuous learning from the traffic patterns, right? And the third case study is something for you to take up. I think like with that we covered most of it, but I just bring this up because this is one of the patents that we were talking about. So this is what we filed when I was in SRM. So this was our intelligent system, right? It was our intelligent agent. So what we built was, we built a machine vision enabled tactical scope, right? So we have seen a lot of scopes. Like basically the idea is, what the general idea that we have of scope is, a scope is mounted on a gun. It gives us more observability. Like if you look through a scope, you can zoom into a target. It'll help you easily like focus on the target, right? But what we did was like we made it a little more better, where you can track your targets, where you can surveillance, you can perform surveillance on the system itself, right? It has sensors. These sensors, basically, if you see, there are different kinds of sensors. There are different kinds of image algorithms that can help you find hidden objects in. And so if you see there is a person sitting behind, you don't need to focus on that person, but it will find that for you. So today AI has become very strong. Back then, it one of our biggest challenges was to like build this entire system on a SoC, like system on chip, right? So it was very difficult to do that. So that's why like that was one of our biggest challenges. We were trying to run ML algorithms. We were trying to we were taking in a lot of sensor data, right? They were like wind speed. What is your wind speed that is happening? So based on that, you can basically have a trajectory of how your bullet could a little bit deviate from its path. So those kind of things, right? We were so this is what our novelty was, that we were building a intelligent smart scope that can adapt based on its system, like based on the wind speed, it can adapt, it can optimize which angle should you aim in order to like for your aim to be very perfect. It can track your particular target. So if they're moving in a certain direction, it can estimate where they will be going to end up if they're in a motion, right? These are the kind of like these are kind of intelligent systems that we came up with.